Shopping for groceries, picking up a prescription refill, and taking your dog to the vet doesn't sound like an ideal Saturday itinerary, does it? You'd rather be hanging out with a few friends, right? So what if you have the squad tag along? Errands aren't fun, but an outside observer might see you cracking up at Ahmed's vegetable puns, giggling as Sophia keeps you entertained at the pharmacy, and smiling as Mateo plays with an adorable puppy in the vet's office. So which is it? Did you have fun, or was it a tedious day of errands? In a way, the answer is both. We encounter the same kind of Schrödinger's cat ambiguity when we examine resonance structures of a molecule. Is the double bond in ozone on the left or on the right? The answer is neither, but also kind of both. In this video, we'll take a look at how we can use Lewis dot diagrams to visualize resonance in a molecule while being careful not to assume that the molecule in question actually exists as it's drawn. Lewis dot diagrams are a fantastic way to visualize how atoms connect in a molecule, but like a lot of our ways of understanding the submicroscopic universe, they don't capture the entire truth. For instance, take a look at these two common examples. A carboxylate anion, which is the deprotonated form of a carboxylic acid, and a peptide bond. In the carboxylate anion, we can see that it's possible to place the negative charge on either oxygen, with corresponding implications for where the double bond is. In other words, given the atoms and electrons available, we can give one oxygen a double bond to carbon, and the other oxygen a single bond to carbon plus a negative charge. It doesn't matter which is which, because the oxygens are equally stable swapping roles. Similarly, in a peptide bond, we can draw the double bond in the amide group as either a C to O double bond or a C to N double bond, although the latter case involves placing charges on the oxygen and nitrogen atoms. As it turns out, those charges are pretty stable because oxygen doesn't mind being negative that much, and nitrogen is equally chill, holding on to a positive charge for a few moments. We'll come back to this in a bit. Whenever we have different ways of drawing the same molecule by shuffling around high electrons, we describe the molecule as having resonance. The different ways of drawing a molecule are termed resonance structures. Now, it's not really the case that sometimes the electrons exist in one double bond and sometimes they exist in the other, because electrons are fast. The actual electronic structure of the molecule is somewhere in between the most stable resonance structures because real electrons are delocalized. They're free to move around without being tied down to a specific location between atoms. An important feature of this idea is that resonance increases stability. Electrons repel each other, so two electrons that are allowed to distribute themselves across the space of two or more different bonds will have a lower total energy than if they were confined to a lone double bond and forced to hang out with each other forever. To see this in practice, let's take another look at carboxylate. The electrons in the carboxylate anion are free to move around between the two oxygen atoms in its structure, resulting in an even distribution. As such, we could draw both the carbon-oxygen bonds in a carboxylate anion with a single bond plus a dotted line, like this, to suggest that we're dealing not with a single bond or a double bond, but a bond halfway in between with a bond order of 1.5. So how do we know this is what the molecule actually looks like rather than flip-flopping from one structure to the other? We can experimentally measure bond lengths. Recall that double bonds are shorter than single bonds. Double bonds are stronger and therefore bind their two atoms more tightly together. When we measure the bond lengths between carbon and oxygen atoms in carboxylate, we do not see one longer bond and one shorter bond. We instead see two bonds of equivalent length. The thing with the 0.5 notation is that it can be really helpful, and in particular, it can be useful as a way to clarify what resonance actually means on a physical level. But it doesn't apply to all cases of resonance. Sometimes one resonance structure more closely reflects the molecule's underlying structure than others might. Let's return to our example of a peptide bond to clarify this point. All things being equal, Lewis structures that minimize formal charges are more favorable. So the neutral amide structure better reflects the underlying structure of the peptide than the alternative structure with a C to N double bond and charges on the oxygen and nitrogen. However, the electron delocalization pattern represented by that latter Lewis structure does make some important contributions to how peptide bonds behave. It stabilizes them and makes them less likely to be hydrolyzed, and it gives them a planar spatial orientation, almost as though there was a C-N double bond. However, this asymmetry between the degree to which each Lewis dot structure reflects the underlying structure of a peptide bond means that it is misleading to represent it using a dotted line with a 1.5 bond order. Instead, the delocalized electrons prefer to be closer to the nitrogen than to the oxygen. Therefore, the electron density is a little higher in the CN bond than it is in the CO bond.